One of the most important things we can do with a telescope is spectroscopy. We can sort photons by wavelength, or equivalently by energy. In this lecture, we'll take a deep dive into spectroscopy. Spectroscopy is our main way to learn about the physical conditions of a star, planet, a nebula, or a galaxy, its temperature, pressure, and composition. You might remember that historically, the advent of spectroscopy in the late 19th century was a major motivation to invent that new term, astrophysics. Let's begin with another look at the spectrum of sunlight. Along with the continuous ribbon of color, we see dark lines. The sunlight is missing certain colors. For example, there's a conspicuous line in the red part of the spectrum and another one in the yellow. We'll be using those two as examples throughout this lecture. The pattern of lines looks sort of random, but not completely random, almost as though it were a secret code. Well, it is a code, and it contains a message, but not from aliens. It's from the atoms and ions in the sun's outer layers. They're broadcasting information about their temperature, abundance, and much more. Those dark lines were first observed in 1802, but the message wasn't decoded until the 1920s. You know why? It's written in the language of quantum theory, and that wasn't developed until the 20s. So we need to zoom in again to the atomic level. Setting aside quantum physics, we can imagine an atom as a tiny solar system in which the attraction is provided by the electrical force instead of gravity. Electrons orbit the nucleus just as planets orbit the sun. The classical theory of electromagnetism says that any accelerating charge will radiate. We've discussed that before. If a charge suddenly starts moving, its electric field develops a pattern of kinks, abrupt changes in direction that propagate outward at the speed of light. Well, an electron orbiting a nucleus is also accelerating, a centripetal acceleration. It feels an inward force. That's what keeps it bound to the nucleus. So, an orbiting electron should emit electromagnetic waves, which carry away energy. In the case of planets, we learned that the total orbital energy, kinetic plus gravitational potential, is minus gmm over 2a, where a is the orbital distance. A similar formula applies to the case of an electron orbiting a proton under the influence of the electrical attraction. The energy is minus eta times e squared over 2a, where eta is the Coulomb constant, and the little e signifies the magnitude of the charge on either the proton or the electron. If the system is gradually losing energy by radiating electromagnetic waves, E is getting lower. It's becoming more negative. That means A must be shrinking. The electron should spiral inward toward the nucleus. That should happen to planets too, by the way. An accelerating planet produces gravitational waves that fly away at the speed of light, as we'll discuss in a future lecture. In principle, this causes planets to spiral inward and crash into the sun, but the timescale over which the orbit shrinks is orders of magnitude larger than the age of the universe, which makes gravitational waves irrelevant to planetary motion. But electromagnetism is much stronger than gravity, and atoms are much smaller than planetary systems. And when you calculate how long it should take for an electron to spiral inward and crash into the nucleus, it comes out to be on the order of 10 nanoseconds. All the atoms in the universe should collapse within 10 nanoseconds. A billion nanoseconds just passed. Are you still here? So am I. So there must be something seriously wrong with that classical model of the atom. What's wrong, of course, is that it ignores quantum theory. Electrons are not just particles, they have wave-like properties too. An electron in an atom is like a wave trapped near the nucleus. Now think about what happens to sound waves when they're trapped in a place, a so-called standing wave, like a vibrating piano string, or the column of air in an organ pipe, the head of a kettle drum. In all those cases, the strong vibrations only happen at certain frequencies. The only wave patterns on a piano string that lead to sustained vibration are the ones where the nodes, the points of zero motion, coincide with the ends where the string is held fixed. For example, when the length of the string is exactly half a wavelength, the vibration pattern is like half of a sine wave with zeros at both ends. And if the length of the string is exactly one wavelength, the wave pattern is a full sine wave with nodes at both ends and another node in the middle. 1.5 wavelengths also works, as does 2 and so on. There's a discrete spectrum of wavelengths, not continuous. That's what happens when you have a standing wave. Now, back to the atom. Because the electron's wave nature, its wave function, is confined by the electrical attraction to the nucleus, it too is a standing wave, and the possibilities for its energy are restricted to a discrete set. Those energies are found by solving an equation, the time-independent Schrödinger equation, which you can look forward to solving in a course on quantum theory. You get a discrete set of energies instead of a continuum, which means there's some lowest energy state, a minimum orbital distance, which we call the ground state. In the context of gravity, that would be like a certain distance from the sun inside of which planets can't exist. For hydrogen, the energy levels of the electron obey a simple equation: minus 13.6 electron volts over n squared, where n is a whole number. The ground state is minus 13.6 eV. Remember, that agrees with the order of magnitude calculation we did back in lecture 2, when we established why atoms are the sizes they are. We can represent those levels on an energy diagram in which the height is proportional to energy. Because the energies vary as 1 over n squared, they bunch up near zero as n increases. For bigger atoms with more electrons, and for molecules with more than one nucleus, the energy diagrams are much more complicated. But the point remains that the energy levels are discrete and there's a ground state. Which explains why atoms and molecules are stable. The electrons in the ground state can't radiate. To do so, they would need to lose energy, but they're already in the minimum energy state. And it also explains the dark lines in the sun's spectrum. You see, an electron can jump from one level to a higher one, but only if it absorbs just the right amount of energy, like from a passing photon, whose energy is equal to the difference between the two energy levels. Suppose there's an electron in the n equals 2 level of hydrogen. To jump to n equals 3, the electron needs to absorb an energy, based on our equation, of 13.6 eV times 1/3 squared minus 1/2 squared, which is 1.89 eV. A photon with 1 eV won't work, not enough energy. And neither would 2 eV. The electron either absorbs a whole photon or not at all. It can't just carve off a fraction of the photon's energy. Since photon energy, E, equals hc over lambda, and lambda equals hc over E, an energy of 1.89 eV corresponds to a wavelength of 0.656 microns, which is in the red part of the spectrum. That's exactly the shade of red that we saw was missing from the solar spectrum. The dark lines are called absorption lines. It's a bit of a misnomer. As I'll explain later, the atoms are emitting those special photons just as much as they're absorbing. The electron can fall back down from the n equals 3 level to 2, releasing a photon with 1.89 eV. Since we know the energy levels of atoms from laboratory experiments and computer calculations, whenever we measure the wavelengths of absorption lines, we can learn the identities of the atoms responsible for those lines. 0.656 microns, that's hydrogen. 0.589, sodium. 0.397, that's calcium, and so on. Each atom produces a whole bunch of lines with a known pattern. It's really amazing when you think about it. Here we are, stuck on the Earth, with no way to visit the stars and bring samples back to our laboratory. But we don't have to. The spectrum of a star is like a barcode that reveals its ingredients. Now, let's look at some stellar spectra in a different way. Instead of rainbows, we'll plot intensity versus wavelength across the visible range of the spectrum. If the Sun were a perfect black body, the spectrum would be a smooth curve, peaking at around half a micron. But a real spectrum has lots of divots. Those are the absorption lines. We see now that the star is not completely black at those wavelengths. There is some intensity, but it's lower by as much as 30% than the surrounding spectrum. We can see that dip at 0.656 microns from hydrogen, and there's one at 0.589 microns from sodium, and lots of others. Let's compare the solar spectrum with the spectra of other stars. For that, we need to use a logarithmic intensity axis to capture the wide range of intensities on a single chart. First, let's pick a bluish-white star, like Mu Andromedae. You can tell it's bluer than the Sun because the intensity rises toward shorter wavelengths, the blue end of the spectrum. And the pattern of absorption lines is different too. We can hardly see the sodium line, and the hydrogen line is deeper. The deep lines at shorter wavelengths are also from hydrogen. They represent jumps from n equals 2 to 4, 5, and 6. So, does that mean Mu Andromedae has more hydrogen than the Sun? And the Sun has more sodium? That's what some astronomers used to think. But the truth is more subtle. A big clue came when the pioneers of astronomical spectroscopy discovered that stellar spectra can be sorted into a single sequence. Here are the spectra of some representative stars in that sequence. As you go from one to the next, the shape of the spectrum and the pattern of lines change smoothly. The spectrum morphs continuously from one to the next. As we work our way downward on the plot, the hydrogen lines go away and the sodium line builds up. We can show this pattern as a chart in which the x-axis is the position of a star in this spectral sequence, and the y-axis is the strength of various absorption lines, how dark they are in the spectrum. At one end, some of the helium lines are the strongest, and then as you move down the spectrum sequence, the hydrogen lines take over, and then later the lines of sodium and calcium rise and fall in strength. At the very end, there are lines from a molecule you might not have expected, titanium oxide. It's closely related to the active ingredient in some sunscreen lotions. So what does that mean? Are the stars at this end of the sequence made out of sunscreen lotion? No. It turns out all the stars are basically made of the same ingredients in the same proportions. What's changing as we move along the sequence is the temperature of the star's outer layers. You see, to produce an absorption line, not only do you need photons with the right energy, you also need a supply of atoms with electrons sitting in the lower energy level, ready to absorb those photons. And the supply of such atoms will depend on temperature. Consider the hydrogen line at 0.656 microns. It's often called the H-alpha line, and it's from electrons hopping between the n equals 2 and 3 energy levels. For that to happen, we need lots of hydrogen atoms with electrons sitting in that second level. And that only happens over a restricted range of temperatures. Now, why is that? Temperature is a measure of the kinetic energy per atom. If the temperature is too low, the electrons will all be stuck in the lowest energy state, n equals 1, not 2. If we raise the temperature, the atoms collide with higher speeds, exciting more of their electrons up to n equals 2. But if we make it too hot, the electron will hop even higher, or would get ripped off the atom completely. When an atom loses an electron, we say it's been ionized. For hydrogen, that takes 13.6 eV of energy. So if the kinetic energy of a hydrogen atom approaches 13.6 eV, it's in danger of getting ionized when it collides with another atom. Putting it all together, the number of electrons in the n equals 2 state will be the product of two opposing factors. The first factor is the fraction of neutral atoms whose electrons are in the n equals 2 state, as opposed to some other energy level. That's a rising function of temperature. In fact, it's our friend, the Boltzmann factor, e to the minus E2 over kT. You might remember that from when we were comparing particles and photons. The second factor is the probability that the hydrogen avoids ionization, and that's a falling function of temperature. To calculate that function would take us beyond the scope of this course, but in case you'd like to investigate on your own, the relevant equation is the Saha equation. The product of those two factors, rising and falling functions of temperature, has a peak somewhere in the middle. For our hydrogen example, it comes out to be about 10,000 degrees Kelvin. For helium, the absorption lines are maximized at a higher temperature because the relevant electron is more tightly bound to the nucleus. Sodium and calcium have weakly bound outermost electrons that produce lines that are strongest for Sun-like stars, 5,000 or 6,000 degrees. So the pattern of lines encodes the temperature. The first person to crack this code was Cecilia Payne, later Payne-Gaposchkin, in 1925. By interpreting stellar spectra with the newly discovered laws of quantum theory, she could deduce the temperature and the composition of a star based on its spectrum. She was the first person to figure out what the stars are made of. In general, they're about 75% hydrogen by mass and 24% helium, with the remaining percent or so from heavier elements, especially carbon, nitrogen, and oxygen. Sodium, calcium, and titanium oxide are only present in minute quantities, but they happen to have electron energy levels in the right places to produce strong lines when the temperature is right. Now let's turn our attention from stars to nebulae. A nebula is an interstellar cloud of gas and dust. There are lots of different kinds, and you find them all over the galaxy. The Orion Nebula is a glowing, colorful, complex cloud that appears in the Sword of Orion. At 400 parsecs away and 7 or 8 parsecs across, it's one of the nearest big star-forming regions, where clumps of gas are contracting under their own gravity, eventually becoming stars. The spectrum of the Orion Nebula looks very different from that of a star. It's totally dark, except for a few bright spikes at particular wavelengths. So what's going on here? What is the key difference between the star and the nebula? It's not temperature this time. Instead, the key difference is density. The density of gas in the Orion Nebula is about 10 billion times smaller than in a star. The low density means that our usual assumption of thermal equilibrium between the atoms and the photons breaks down. The atoms in the nebula are in thermal equilibrium. They collide and share energy, achieving a uniform temperature of about 10,000 degrees Kelvin for the case of Orion. But photons don't interact as frequently. If an atom inside the nebula emits a photon, it won't always crash into another atom and get absorbed. There's a good chance it'll just sail off into space. So what happens in the nebula is this. Collisions between atoms push the electrons up to higher energy levels. They eventually fall back down and emit photons, which then escape the nebula and land in our telescopes, having never interacted with anything during their journey across 400 parsecs. The photons we detect, then, only have the energies that were emitted by electron transitions within the atoms of the nebula. And we call that an emission line spectrum. The situation is different in a dense medium like a star. There, a photon emitted by one atom almost always gets absorbed by a neighboring atom. Then that atom will re-emit another photon, but not necessarily with the exact same energy. The high density and the high frequency of collisions cause the energy levels to be blurred out. And photons can also get scattered from charged particles, electrons or ions, which alter the photon's energy in a continuous way, producing more blurring of the spectrum. We can imagine the photons as pinballs getting knocked around in a pinball machine. All the bumpers, flippers, and kickers are the atoms. The directions and energies of the photons are constantly changing. So given enough time, the atoms and photons come into thermal equilibrium, and the photons can attain a Planck spectrum. The little bit of light that does leak out will have the spectrum of a continuous rainbow. Quantitatively, the key concept separating the nebula and the star is the mean free path, the average distance a particle can travel between interactions. As an example, the mean free path of a visible photon in air might be 10 kilometers on a really clear, dry day. That means photons from 10 kilometers away can propagate unimpeded all the way to your eye. The mean free path of the molecules in air is much shorter. It's on the order of 1/10 of a micron. They're constantly colliding with each other. The photon mean free path is so much longer because visible photons don't have the right energy to be absorbed by nitrogen or oxygen. In general, a medium is transparent if its spatial extent is substantially smaller than the mean free path of photons, like a piece of glass, or a tank of water, or a diffuse interstellar gas cloud like the Orion Nebula. Astronomers don't use the term transparent, though. The technical term is optically thin. The idea is that from the point of view of a photon, the medium is thin. There's a little chance the photon will hit something when it goes through. Conversely, when the spatial extent is larger than the mean free path, we say the medium is optically thick. In ordinary English, we'd say it's opaque. A related concept is optical depth. That's defined as the distance through some medium divided by the mean free path. So it's a dimensionless number, often written as tau. As an example, imagine we're walking in the forest in a thick fog, where the mean free path is only 10 meters. The optical depth of the sight line to a tree would be the distance to the tree divided by 10 meters. Trees that are closer than 10 meters are at an optical depth less than 1. Within that range, photons originating at the tree can reach our eyes without getting scattered. Much farther than 10 meters, the optical depth is greater than 1. Photons that come from way back there get scattered multiple times, so by the time they reach our eyes, they're arriving from a random direction. All we see is a white wall, which appears to be located about 1 mean free path away at an optical depth of 1. The lesson is, whenever you're peering into an optically thick medium, the photons reaching your eye originated from an optical depth of order 1. That's what we mean when we refer to the surface of Jupiter or the surface of the Sun. Both objects are gaseous spheres, there's no solid surface, and the gas gradually gets denser as you go from the outside to the inside. But we can define the surface in such cases as the level at which the optical depth is of order 1. The more technical term is the photosphere. For example, when we refer to the effective temperature of the Sun, what we mean is the actual temperature of the gas that's at an optical depth of 2/3. The reason it's 2/3 instead of 1 is that a more detailed calculation shows that with that definition, the effective temperature obeys the equation that we expect for a spherical black body. L equals 4 pi r squared times sigma t to the fourth. With all these definitions in place, I can spell out the basic rules of spectroscopy. They're called Kirchhoff's laws. Number 1 is that optically thick sources emit a continuous Planck spectrum. That's because the density is high enough for the photons to reach thermal equilibrium with the atoms. Law number 2 is that optically thin sources produce emission lines, like the Orion Nebula. Photons don't interact with atoms on their way out, so there's no way for them to reach equilibrium. And number 3, if you have a hot, optically thick source surrounded by a cooler, optically thin layer, that's when you get an absorption spectrum. This third one is the most interesting case, and it requires some more explanation. Stars are hotter and denser on the inside than the outside. So a star is an example of a hot, optically thick source, the stellar interior, surrounded by a cooler, optically thin layer, the photosphere. The crucial point is that the mean free path is not the same for all photons. It depends strongly on the wavelength. Photons with a wavelength that's just right to be absorbed by the surrounding atoms have a much shorter mean free path than photons with some random wavelength. For example, in a star with a photosphere at 10,000 degrees Kelvin, the mean free path at 0.656 microns is much shorter than at 0.6 or 0.7 microns. Photons with that specific red color can't propagate as far as other photons. When we point our telescope at the star, we see down to an optical depth of 2/3, but the actual depth in kilometers, at which the optical depth is 2/3, depends on wavelength. At 0.656 microns, the star is more opaque. We can't see as far down into the interior. That means the photons of that wavelength that reach our telescope originated in a shallower, cooler layer of the star. And the blackbody radiation from that cooler gas is less intense than the radiation from deeper down. So at 0.656 microns, the star appears fainter and darker than it does at adjacent wavelengths. We get a dark line in the spectrum. If we could somehow resolve the stellar disk, and if we had special glasses to view the star at any wavelength we want, when we look at 0.656 microns, the star would look fainter and slightly bigger by maybe 1,000 kilometers because the photosphere isn't as deep. It occurs at a higher elevation from the center of the star. Now you can understand why it's a little too simplistic to say the dark lines come from absorption. It's true, those photons are getting absorbed, but they're also getting emitted at the same rate. It's more accurate to say the dark lines are there because the star is more opaque at those wavelengths. We can't see as far down into the stellar fog. And you're also ready to understand another interesting phenomenon. An image of the sun with an appropriate telescope shows that it gets fainter near the rim of the circle, the so-called limb of the solar disk. And this is not an optical illusion. The radiation from the limb of the sun really is less intense than the radiation from the center of the disk. This phenomenon is called limb darkening. Now, your first reaction might be, well, that's just because the sun is a sphere. It's not a flat circle. What we're seeing is the shadowing effect that you always get when you shine a light at a sphere. But wait a minute. We're not shining a light at the sun. The sun is shining at us. It's glowing from within, sending power equally in all directions. It's not the spherical shape of the sun that causes limb darkening. In fact, you can prove that a uniformly bright sphere doesn't show any limb darkening. From any angle, it looks like a uniformly bright circular disk. If you don't believe me, you can buy yourself a luminous decorative sphere. You can find them on the internet. People use them to spruce up their backyards and gardens, and they don't show limb darkening. Instead, what causes limb darkening is that the sun, like all stars, is a gaseous sphere, hotter and denser on the inside than the outside. When we look toward the center of the sun, our line of sight pierces the sun nearly perpendicular to the photosphere. The photons that come to us from that direction originated at an optical depth of about 2/3, corresponding to a certain depth in kilometers within the sun. But when we look toward the limb, our line of sight skims the surface. If we follow that grazing line of sight, we reach an optical depth of 2/3 at a higher altitude, further from the center of the sun. And at higher altitude, the temperature is cooler and the radiation is less intense. That's why we get limb darkening. It's a neat effect, and it's a useful way to test models for the sun's photosphere. By observing the limb darkening in different colors, we can learn about how the temperature increases with depth and how the overall opacity of the sun varies with wavelength. And with that, we conclude our overview of spectroscopy. We've seen that spectroscopy allows us to take the temperatures of stars and see which atoms and molecules are in nebulae. And as if that weren't amazing enough, later we'll see that we can do even more. Spectroscopy allows us to measure the masses of stars and black holes, detect exoplanets, and even determine the expansion rate of the universe.